All right, thank you very much for that kind introduction. So I'm going to speak to big data, to solutions from the perspective of my discipline, and that's animal breeding and genetics. The genetics part is probably somewhat intuitive from a high-level overview to most of you. Animal breeding, though, when I say that, it's sometimes misunderstood, and people assume that I work in a field called animal breeding. That must inherently mean I have something to do with reproduction and reproductive physiology, and that's not true, right? So my knowledge of beef cattle reproduction is that when a bull really loves a cow, then roughly 280 days later, a stork brings a calf, okay? And I think that's really all you need to know about reproduction. Animal breeding, though, what I do is really the discipline that helps us inform which bull we introduce to which cow at the social, all right? So in other words, my interest is improving a population of animals using genetic selection tools. The tools that we have to do that have evolved considerably over really the last several decades, and now in the genomic era have evolved at an unprecedented pace. So big data, everyone talks about big data now in the agricultural sciences, and I'm going to try to frame that in terms of what we deal with in animal breeding and genetics. We have data that comes from a lot of sources, so from farms or ranches all across the U.S. and in many cases across the world. And some of those data resources are large, thousands of animals. Some of those data resources are relatively small. And the number of animals, the number of data points, so phenotypes or characteristics per animal, plus all the new genomic data is constantly mounting. And our challenge is to somehow turn that data into more informed decisions. Right? So there's a difference between data and information, there's a difference between information and knowledge, and there's a difference between knowledge and actually taking action and making an informed decision. So that continuum, honestly, is the challenge that we're working with, and part of that process is actually developing tools that can be used to inform which animals should be parents for the next generation. So at the crux of it, what we're trying to do is take phenotypes, which we may measure 20 or 30 characteristics per animal. Combine that with pedigree, which is really ancestral relationships, kinship among animals, which may include tens of millions of animals that all have those phenotypes measured, along with genomic data. And so those populations may have hundreds of thousands to millions of animals genotyped, and each animal genotyped has been measured with maybe between 10,000 and 250,000 DNA variants. So I think over there she's doing the multiplication to tell you exactly what big data is in our context. And it's all distilled down into a genetic prediction, so a numerical representation of an animal's worth as a parent for a given trait. So admittedly, that takes a wee bit of statistics. And I'll pause so she can copy down that equation. So genetics and statistics, quantitative genetics, what I do are intimately intertwined, and they have been really since the inception of those two disciplines. So our task is to take all of that data I mentioned, plus information about how they were reared, where they were born, what year they were born, what season they were born in, how they and their cohorts were managed, and try to inform the prediction of which one of these two bulls we should choose to be the parent of the next generation. And we're becoming more accurate at that all the time due to the growing body of genomic data. So the holidays are coming up, Thanksgiving, right? Some of you are probably going to host a lot of relatives and friends there. And some of you may think, I'm not excited about it because Grandpa so-and-so is going to be there, right? And he always smells, and he gets into the wine too much, and he tells off-colored jokes, and I can't believe that I'm actually related to him. Here's the good news. Really, you may not be. And now you're thinking, damn it, I knew Mom had been lying to me for years. Note, at the DNA level, your relationship to that annoying grandparent may be minuscule. So our expectation is that your relationship to any grandparent is a quarter. You share a quarter of your genome with that grandparent. But we've always known theoretically that could range between 0 and a half. What DNA information has allowed us to do is refine our estimates of the relationships between animals. Because we can refine that relationship, we're better able to predict the genetic merit of the next generation because we know how much of their genome came from ancestors that we know an awful lot about. So what does that do? That increases the accuracy of our genetic predictions, those things that we use to rank potential parents. Because we increase the accuracy of those genetic predictions, we're able to make faster genetic change. So faster genetic change for traits like the efficiency of feed utilization in livestock. Faster genetic change related to reducing the susceptibility of disease. Faster change related to the eating experience, those traits that impact the eating experience of the people that actually buy our product. So that's what we're all about, producing tools that are more accurate, that can increase our rate of genetic change. So here's empirical data that shows that. This is actually swine data. These are grandparent individual relationships. The red line is our expectation, a quarter. But you'll see it ranges from about a 0 to a half. So genomic data has been able to empirically prove what we always knew via theory. So what are the problems and opportunities? Well, we've got a lot of traits. So I mentioned maybe 20 or 30 characteristics that may be economically relevant to an individual agricultural enterprise. Not all species are equally positioned to take advantage of the growing amount of data, right? So swine and poultry companies, fairly integrated, very few decision makers. They can all go in a common direction fairly quickly. Beef cattle, a lot of ranchers, right? A lot of independent decision makers, and as a consequence, sometimes it's harder to adapt technology as rapidly. The other thing is we're doing whole genome sequencing on animals. So now instead of maybe 250,000 DNA variants, we're measuring millions of them. And the question is, which ones are important? How do we reduce the complexity of the problem? So what shows reducing the complexity of a decision better than a very complicated schematic, right? So imagine this. I'm a young rancher in Bridgeport, Nebraska. I've got cows to manage all day. I've got row crops to take care of. I get home at night. I've got a young family. Maybe my wife works at night. And I've got to decide which bulls I'm going to buy to introduce to my girls at the social, right? The cows. How am I going to spend time doing that in an economic framework, in a framework that's going to make money for me? I'm not a geneticist. I am. The hypothetical person I'm talking about is, right? Well, this is the vision of how we go from big data to knowledge to actually the accuracy of a decision. I sit down behind my computer at night. I say, here's information about where I live, the cost of my inputs, how I market my animals, the breed of animals I have, enter, and then in the background, we grab data from all these organizations, all of that big data, and we amalgamate that together using the parameters that person estimated, and we calculate an index that puts all those traits together in the framework that's most economically important for them, and we rank all the potential candidate sires based on that economic index. So that's the idea of how we take a lot of information and make a decision quite simple to use. Where we have made a mistake pervasively over the years is the thought that we can just stop at tools and people figure out how to use the tools. That's a mistake because we assume that they have the same level of knowledge that we have and they have the time to investigate it. We've got to go a step further and actually help them take the decision based on what's economically relevant for them. So the data source is constantly growing. If all we cared about, Steve, if all we cared about was generating publications, we could stop collecting data right now and just focus on analyzing the data we have. The problem with that, though, is we wouldn't keep pace with the industry that constantly needs better solutions. So that's why we allow the data to continue to grow, try to keep up as best we can. So turning data into decisions requires really an integrated approach: computational sciences, statistics, biology, and industry knowledge. I would argue that the UNL, Animal Breeding and Genetics group, is well positioned to go from data to decisions. So one is through partnerships, inherently with industry, with colleagues here in statistics department, and the U.S. Meat Animal Research Center, which if you guys don't know about that, that is absolutely invaluable resource just roughly 90 miles to our west. We're actively engaged in taking all those millions of DNA variants and finding the ones that cause some animals to become sick or remain healthy despite disease challenges, and merging all available data to improve the genetic prediction and ultimately improve efficiency of meat animal production and consumer satisfaction. So in a nutshell, that's why we do what we do and why we do it. And I have no idea how long I took, but I know I'm done. So thank you.